pretty long problem ahead, so we're going to dive in, and we will have to make reference to a couple things that I didn't pay attention to until this question. So let's go ahead and try it out. What we see here is that a particle of charge Q1 is at rest at the origin. A second particle of charge Q2 moves along the z-axis at a constant velocity v. Find the force F1 on 2 t of Q1 on Q2 at time t. Find the force F21 of t of Q1 on Q2 on Q1 at time t. Calculate the linear momentum P of t and the electromagnetic fields at time t. D. Show that the sum of the forces is equal to the minus the rate of change of the momentum in the fields, and interpret the results physically. Okay, well, let's draw out what we have. Q1 at rest at the origin, as stated. All right. Q2 moving at speed v along the z-axis. So clearly then, if we're trying to see what the field is going to do at some point in space, right, we have theta coming from the little r and Q1 to the field point. Then we have big R due to the moving charge, which forms theta prime to the z-axis. Okay. Again, these geometric definitions are going to have to come into play at some point, so be readily aware of the mess that's about to happen. All right. So just like a question not too long ago, since Q1 is at rest, we can use Coulomb's law, which I think was the last question. I don't honestly remember. But anyways, since Q1 is at rest, we can use Coulomb's law. So F1 of 2 is equal to Q2 times E1, and E1 is just a static field, hence why we use Coulomb's law. Okay, cool. We see that we have 1 over 4 pi epsilon naught Q1, Q2, and then instead of Z, we have VT squared, since that keeps growing at distance, that separation distance. The electric field of Q2 at Q1, where R vector, capital R vector, is equal to negative Z hat is equal to E2, Q2 over 4 pi epsilon naught times the constant velocity here. Clearly, since we're dealing on the same line, sine of is equal to the sine of 180 degrees, because the V is moving forward up the z-axis. Meanwhile, charge 1 is at the origin below it 180 degrees. So, that being said, that goes to sine of 180, which is 0. And then, so that whole denominator goes bye-bye. And we love seeing that. Holy moly. We love it. All right. So, anyways, we have as a field, negative Q2 over 4 pi epsilon naught, 1 minus V squared over C squared, divided by V times T, the whole thing squared in the Z direction. Multiply that by Q1 to get the force 2-1. And we see that we're left with negative 1 over 4 pi epsilon naught Q1, Q2, times 1 minus V squared over C squared, divided by VT squared in the Z direction. So no, Newton's law does not hold. V12 does not equal V21. We saw that before with that the throwback to chapter 8, which is actually 2 questions ago, or 3, whatever. I'm losing track, having too much fun. But now we need to find the linear momentum. Okay, so the linear momentum of the field, the linear momentum is given by P is equal to epsilon naught E cross B d tau. Here, though, superposition says that E is equal to E1 plus E2, whereas B is equal just to B2. Again, at the origin being static, we don't have any current, so we don't have any magnetic field. Okay, that's how we determine that. But now what we need to do is find what is E cross B. Well, if that's the case, we have E1 plus E2 cross B2, and now we need to distribute that. But the latter, which is in red, when integrated over all space, is independent of time, and we only want the time-dependent part, okay? So we really don't care about what E2 and B2 does, because there's no time dependency there once integrated across. Save ourselves a lot of work there. And the reason why is whenever we take the cross product, we get V cross R cross VT split that cross product up with back cab and all that other stuff. Since we have a static one there for the origin, that goes bye-bye. And then we're left with R cross R, which is 0 in my little quick scribble notes. But yeah, no, that red goes bye-bye. So all we're concerned with is E1 cross B2. All right, so let's go ahead and dive in then. The momentum, therefore, with E1 given from the first part and B2 given the fact that we have 1/c V cross E2. And again, these cross products make life a living nightmare sometimes. So be aware of that with these things. E2 is equal to the form of moving constant velocity. In general, we have to use the prime coordinates now, not just for the forces in these particular setups. So we got to be careful, of course. Here's how the geometry is defined for all the situations. Let's take a look. Sine prime is equal to R over sine theta, big R. That comes from law of sines, just to keep things ahead of schedule. Let's see what else. And now it's just a matter of putting these darn things together, and it is. No, my goodness, none of this is going to be nice to deal with, to be quite frank. So simplify down. We're trying to take that R out of that capital R out of E2, and that's where we're spending most of our time, is trying to simplify that. Now we notice that the cross product of V cross R minus VT, well, no one really cares because R cross V cross R is equal to RV sine theta in the fiat direction. We like that. But we know that V cross V is equal to 0. So we're good there. Yeah. So, okay, cool there. We like that. B2, therefore, is equal to, once all these cross products are done with, is equal to this thing where we have R squared is equal to, big R squared is equal to little r squared minus 2RV t cosine theta plus VT. Again, think about law of cosines there. Make your life simpler. Now this horrendous looking integral is coming to light now that we have E1 and B2. Holy moly, this is not nice looking at all. Notice that in the red I have some cancellation factors just to help us tidy things up. And then we'll push through all the constants out. So Q1, Q2, factor of V, and then 1 minus V squared over C squared over 4 pi C squared epsilon naught. Oh my goodness, it is gross. What we're left with is R cross phi hat times theta, or sine theta, over little r bracket big R squared minus VR sine theta divided by C squared to the 3s power d tau. Okay, whatever. But what we know about this simplification is that R cross phi hat gives us a negative theta hat. And so we see what that's written out in terms of its Cartesian unit vectors. Again, these unit vectors are nothing but a mess, so be careful once again. And if you recall from chapter 8, the x and y components integrate to 0, so all that we're left with is the z component. Okay, we can deal with that. That's definitely a not disturbing, but a nice fact of these symmetries with these odd things that cancel everything out. So let's do it. And we take advantage of it. So with that being said, we're left with just a sine theta z hat. And d tau, of course, is equal to r squared sine theta dr, d theta d phi. Of course, we're going to push the d phi integral through. That just gives us 2 pi. We know that. We've seen it. That little r cancels with the 1 in the denominator, and we can, push whatever we need to through and try to simplify and tidy up as much as possible. I know it's not always possible, but now we're going to substitute in that big R squared, and we see more work to be done with these R's here. So we combine like terms, factor that out. As I stated here in the problem, this is undeniably a mess. Consider the R integral first, and then we are able to reference the CRC tables, and we see that we have this form here, which looks pretty similar to what we have for the R integral. And now it's just up to us to form match. Here, x equal r, so a is equal to vt squared. B is equal to negative 2v naught, or vt cosine. And c is equal to 1 minus v squared over c squared sine squared theta. All right, so if we substitute back in before the theta integral evaluation, we need to simplify quite a bit. And so we do. Tidy up, tidy up, tidy up. I'll let you look at the math. That cancels down as much as possible. We factor out what we can, and then we simplify. I try to color coordinate so you can see where all the simplifications are coming, and the eventual separation in the brackets. Once we substitute this in, we see that we can actually cancel out quite a bit, which makes us really excited. Yeah, now all we're left with is the theta integrals, and once again, when we let that u sub happens, what we see is pretty nice. We see that that integral is odd, and we're over symmetric bounds, and so that goes to 0, and we save ourselves a headache. Yes, we like saving headaches. I mean, unless you like them. I don't want to speak for you, but saving a headache is nice. So yeah, now we see that after we tidy up that split from the integrals, we get the momentum in the fields is mu q1 q2 over 4 pi t in the z hat direction. Wow, what a mess. So does the sum of forces F12 plus F21 equal the rate of change of momentum? Well, let's apply it. Let's add them up. Let's add up the forces here. If we do that, you see we get some cancellations of common factors. After the 1's cancel, the v's will cancel, and we're left with c squared. But does that equal the rate of change of the momentum that we see? The negative signs cancel from the power rule on the t. And once we substitute in c squared for mu naught epsilon naught, we get the epsilons cancel. And yeah, we're left with the exact same thing. Wow, okay. For as messy as this thing was, that's a very nice result.